Hello, everyone. The title of this presentation is on distributed storage allocations of large files for maximum service rate. And this work is with my advisor, Amina Sujani. And this work is published in Allerton Conference 2018 with the same name. Distributed storage systems are an integral part of computing and content providing environments. For example, cloud data center, fog systems. Like in this figure, the user wants to access the file on the servers. And the user has two objectives. The first is he wants high probability to get the file. And the second is he wants to get the file fast. Here, it's measured by the system service rate. The system itself has some limitations. The first is the storage is constrained, and the second is nodes may be down, and the third is the nodes may be too far to be accessed. And I will explain this limitation later. Right now, let me describe the problem. Here is the example. Bob wants to buy bread in the shop, and the bread was $3. And here, Bob can select any two out of the red pocket, which has some money. So right now, he can access the first one and the fourth one. In this way, he can get $4, which in this way, he can buy the bread. But the thing is, if he access to the second one and the fourth one, he can only get $1, so he cannot afford this bread. So the problem here is how to allocate the money. Our target is Bob has enough money to buy the bread with high probability. And second is Bob can get the money fast. With this example, if Bob can take any two red pockets, we can easily to calculate in this allocation way, he will get enough money with the probability 2/5. And here the time is T1. If we allocate the money in this way, and the probability here changed to the 3/10, and the time equal to the maximum of T1 and T2. After knowing this example, let's see the general DSS model. First part is coding. We have a file which has k data blocks. We can encode these data blocks into m times k data blocks. For example, how we code it. If the file has two blocks, A and B, after coding, we can get is A, B, A plus B, and A minus B. If the user can get block A and block A plus B, so he can recover the B by using the A plus B block minus block A. In this way, the user can recover the file from any two out of the four coded blocks. So the benefit of the coding is it can improve the reliability. It can also increase the download speed. Second, let's see the allocations. After we get these coded data blocks, we can split these blocks into several parts. Like in this way, we can just put the two blocks into the node one, the first node, and the second block into the third node, and so on. We can see that there is no storage constraint per node. And after the allocation, let's see the access model. The user can access to some of these nodes. Like in this example, the user can access 3 nodes. When the user accesses to the first node has content but not accessible. Like maybe the node is down or too far to be accessed. And for the second one, it can be accessed, but it doesn't have any node. For the last one, the user access, it can access the data and it has the content. So when the user can recover this file, the user can reconstruct the file if he receives k or more coded blocks. In fact, this problem can be formalized as the allocation optimization problem. Like in this way, we can maximum the probability of the successful recovery, and also we can maximum the system service rate. Here we have two questions. First, what are the optimal allocations of probability and service rate? Second, do the two performance objectives have the same optimal allocation? For these two performance objectives, as we can see that the probability, that means the high probability to get the file, as we mentioned at the beginning of the slides. And for the service rate, it is to get the file fast. But we have some difficulties for this optimization. First, it is too many random variables. Like in the problem, we have the variable x1 to xn. And second, the formulas of probability and service rate are hard to find. Therefore, we need to simplify the general model. For the allocation model, we use the quasi-uniform allocation model. And for the access model, we use the fixed size access and the probabilistic access separately. First, let's see the quasi-uniform allocation. It is a special case and it's still very hard. Here, when we have the coded blocks, we uniformly split into L data blocks, and we put each one into the node, and then you can see that all the node, it has the same amount of blocks or has no blocks. In this way, our goal is to find the optimal alpha. Here, this alpha parameter is equal to k over L. So for the allocation parameter, what we can understand like this way. When alpha is smaller, it means to concentrate the blocks into smaller storage nodes. When it's larger, it means spread the data blocks into more storage nodes. And when alpha reaches to 1, it means the minimum spreading. And when it reaches to the n over m, it's the maximum spreading. Here is the example of the minimal spreading and maximal spreading. For the minimum spreading, each node will have L equal to k blocks. Why is equal to k? Because we only need k blocks to recover the file. And for the maximum spreading is for every node will have some amount of blocks. For the access model, let me first introduce the fixed size access model. Here, the user can only access R storage nodes randomly. In this example, R equal to 3. And all the storage node which is accessed will respond to the user. For the second access model, probabilistic access model, the user can access all of the n nodes, but each node can be accessed, but it will respond with a probability 1 minus p. And now we can simplify the allocation problems in this way. For this two optimization problem, we only have one parameter alpha to optimize. And now I will introduce the performance objectives, the probability of successful recovery, and the system service rate. First, let me talk about the probability of successful recovery. Let's see this example. Here, in this example, there is no redundancy introduced to the file, so m equal to 1. And we use the fixed size access model with r equal to 2, which means the user can access 2 out of the 3 nodes. We define the A1, A2, A3 are subsets of nodes. The first figure on the left is the user access to the subset A, which has the node 1 and node 2. And then second figure, the user access to the subset 2, which has node 2 and node 3. And the third figure, here we can use it to calculate the probability the user access to the A1 is 1 over 3, and it is equal to the A2 and A3. But when we consider about the successful recovery, then we can see that only the first figure, the user can recover the file, and the rest of the two, the user cannot. Therefore, the total probability of successful recovery is 1 over 3. Based on this example, what we can get the formula of the probability of successful recovery. And we can get two formulas. One is for the fixed size access model. One is for the probabilistic access model. Now let me talk about the service rate. We define the service rate equal to 1 over the expectation of download time. Like in this example, there are n nodes, and each node has the same amount of coded blocks. And the user needs blocks from any W nodes. For each node, the download time follows the same distribution. So when the user stop, it is when the user receives the block from any W nodes. So the time is the W's order statistic. After knowing this, we know the service rate is 1 over the expectation of this order statistic. Here we use two slides to explain the definition of the order statistic, but in this presentation, I don't want to go deep into these details. After knowing the knowledge, then we can introduce the system service rate. Here is the example. This example is also a fixed size access model with the R equal to 2. You can see that only the first figure, the user can recover the data blocks. So the service rate will be the 1 over the expectation of the time, as we mentioned in previous slides. For the rest of the two scenario, the service rate is equal to 0. And as we know that the probability that set A is accessed is 1 over 3, and it's equal to the other two scenarios, then we can get the total DSS service rate is in this formula. Let's consider about the download time model. For the download time, it relates to the size of the file. For a small file, we only consider about the machine time. For a large file, we need to consider about the transmission time of the file. And also, maybe we need to consider both machine time and transmission time. So what is the machine time and transmission time? The left figure shows the case of the machine time. When the user sends the request to the storage node, and the storage node needs to spend some time, T1, to handle this request. And for the rest figure, after handling this request, the node can send the blocks to the user, and then it will spend some transmission time, T2 here. For a small file, it has been studied in the Inuri's paper in 2016, which used exponential download time, which is loaded independent in both access models. So what's that mean? Like in the left figure, the storage node stores the whole file. On the right figure, this node will store just 1 over b fraction of file. But the download time will follow the same distribution. Then the result will be like in the right figure. No matter for the whole file or the 1 over b fraction of the file, the download time, they are same because it's only dependent on the machine, and the transmission time can be ignored. Based on this assumption, the optimal system service rate is always reached at alpha equal to 1. Here, alpha equal to 1 means the minimum spreading allocation. For a large file, we cannot simply use exponential download time. Here, in our paper, we use the scale exponential download time. If the node store the whole file, the download time will follow the exponential with the parameter mu. But if the node stores 1/b fraction of file, then the download time follows the exponential with the parameter b times the mu. So the difference is shown in this figure, that if the node stores less fraction of the file, the download time will smaller. We also use the shifted exponential download time. For the node stored whole file, the download time follows shift exponential with the parameter mu and shift delta. And if the node stores 1/b fraction of file, the download time follow the shift exponential with the parameter mu and the shift delta over b. In this way, if the node stores a less fraction of file, the download time will be smaller. Right now, let me introduce the system performance for the fixed size access model. It has a theoretical analysis and simulation analysis. Recall that for the fixed size access model, the user can access any R out of these n nodes. And this alpha here is the allocation parameter. When alpha is small, it means concentrate the data, and when it's larger, it spread the data to more nodes. In claim 1, we can find the system service rate for the fixed size access model and the scaled exponential distribution. And from this formula, what we can have is the theorem 1. In theorem 1, we know that the optimal service rate isn't always reached at alpha equal to 1, which means minimum spreading. From the proof, we can see that the two regions are not always exist, which means for some scenario, the minimal spreading is always optimal. And also we can see that there's a big gap between these two regions. So for this part, we can improve this result in the future. From the proof, we can also have a conjecture 1. When R is small, the mu S1 is more likely to be the maximum. When R is large, the maximum mu S alpha is not at 1. And we can also see the optimal alpha is increasing with R, like in this figure. And now let's see the simulation result. The left two figures are average service rate versus the alpha under different m. Here m is the redundancy level. And the left figure is the scale exponential, and the middle figure is the shifted exponential. The red figure is probability of successful recovery versus alpha under different m. And we can see that the optimal points are different. From this figure, we can have the result is for the service rate, small storage constraint scenario, we need to concentrate the coded blocks, which means when m is small, the minimum spreading is optimal. And when for the large storage constraint scenario, spread the coded blocks is better. And we can have similar results for the probability of successful recovery. In this figure, we also consider the average service rate versus alpha and the probability of successful recovery versus alpha. But here is under the R is the number of access nodes. From this figure, we can have the result is for the service rate, the less access node scenario, we need to concentrate the coded blocks. For more access node scenario, we need to spread the coded blocks. And for the probability of successful recovery, we always need to concentrate the coded blocks. Here, in this figure, we can also test our conjecture one. We can see that the optimal alpha is increasing with R. Right now, let's see the analysis for the probabilistic access model. We also have the theoretical analysis and simulation result. Here, recall that for the probabilistic access model, the user will access all the n nodes, and each node will respond with a probability 1 minus p. And also, we want to find the optimal alpha. In the claim 2, we can get the formula of formula for the system service rate and the scaled exponential. And from this formula, what we can have is theorem 2. In this theorem, we know that the optimal service rate isn't always reached at alpha equal to 1, which means minimum spreading. To prove the theorem 2, we can also find two regions. This time, we find the region for the P, that some region that alpha equal to 1 is maximum. Sometimes it's not. And from the proof, we can also have a conjecture too. When P is large, the mu S1 is more likely to be the maximum. When P is small, the maximum mu S alpha is not at 1. And the optimal alpha is decreasing with increasing P. For the simulation result, we have the average service rate versus alpha and the probability of successful recovery versus alpha under the redundancy level M. What we can see from the figure is for the service rate, for small storage constraint scenario, we need to concentrate the coded blocks. For large storage constraint scenario, we need to spread the coded blocks. And for the probability of successful recovery, we can have the same conclusions. In this figure, we have the average service rate versus alpha under the different probability P. Here, we only have the scaled exponential distribution, and the result that we can have from the figure is for the service rate, small field access probability scenario, we need to spread the coded blocks. For the large field access probability scenario, we need to concentrate the coded blocks. And for the probability of successful recovery, we always need to concentrate the coded blocks. And from this figure, we can also see that the conjecture 2 is true, that the optimal alpha is decreasing with P. And in this figure, this figure is for the shifted exponential distribution. In fact, we can have a very similar result at the scaled exponential scenario. Thank you for listening.